So you've been working on projectile motion problems with what we call horizontal launch, where something falls off a table or is just launched sideways some way somehow, and we've asked you to find some information about falling and speeds and distances and so forth. Well, today we're going to go and embark on what I call the full launch, where you're going to have an object kicked or thrown or launched at an angle, and then it's going to travel in that nice parabolic shape, a nice arc over level ground, and land somewhere down the field or over the ocean or wherever you're launching the object. So I can ask you a bunch of things. I can ask you, well, how long did it take to go from launch to when it landed? They call that hang time. What was the distance between where it was launched and where it landed? That's called the range. How high did it go at maximum height? And you can also ask, what's the velocities along any point really along this path? So let's take you through the basics. Let's take you through some pitfalls so that you can get started on trying to figure out how to analyze these problems. The first thing is, okay, and 9 times out of 10, we're going to give you the starting velocity. What's the velocity that this thing is launched into the air? There are some problems where they'll actually ask for the initial launch speed or launch velocity from other information. You can figure that out, but typically those problems are a little bit more on the difficult side. So to ease us into it, I'm going to give you a launch velocity. So somehow, some way, we launch something. Again, you can kick it, you could throw it. It could, have a rocket. Who knows? Well, this particular example, we have 10 meters a second, and it's going to be launched at 36.9 degrees above the horizontal. Now, I'm using this specific angle because it works very well with finding sine and cosine values. The first pitfall is that students think, oh, well, this thing is launched at an angle, so I'm going to go here, it's going to go up to here, and then you're going to go down here, and they're going to make this kind of internal triangle, and they're going to say, oh, it was launched here at 36.9 degrees, and so the object, traveled this way, hit a maximum height. No, absolutely not. This use of this, what I call the internal triangle, to help figure out distances, and no, absolutely incorrect. So none of this usage of this internal triangle, and I'll tell you why. What we need to understand is if this object were launched from the ground or wherever it's being released from, if it's launched at its appropriate angle, and it were launched in space, it would move in this line forever because gravity would not be taking effect. And so once it is launched and gravity begins to pull it downward, then this parabolic path has to be under that initial launch vector. So that initial launch vector cannot be inside the arc. No way. If we understand that, we can, of course, put in the angle 36.9 degrees. Now, we need to know that because this is at an angle, and that means we're going to have to use components. Because now, once it's in the air, as you saw with the previous video with the track and the launcher, this is now motion in 2 dimensions happening simultaneously. We're going to have up and down motion, we're going to have sideways motion. And so I need to take this initial launch vector, launch velocity, and break it into components. And that's really your first move.